welcome back to the deep dive. You know that feeling when you're looking at a huge project, maybe it's launching something new, maybe it's just, I don't know, big life change, and you think, where do we even start?
Yeah, that feeling, that sort of paralysis, that's exactly what we're tackling today. We are deep diving into what's really a toolkit for handling complexity, computational thinking, or CT.
Right. And CT, it often gets pigeonholed, taught just to coders, which honestly is a huge mistake, especially for you listening. Our sources really hammer home that CT is fundamentally a way everyone can solve problems.
Exactly. It came out of computer science, sure, helping engineers wrestle with massive software projects. But the core idea, taking any overwhelming problem and breaking it into steps you can actually manage. Predictable steps. It's just a structured way to think about, well, anything complicated.
Think of it like getting leverage on the problem.
That's a good way to put it. You break it down, you spot the patterns, you filter out the noise, and then you map out the instructions. So today we're going to walk you through the 4 key pieces: decomposition, pattern recognition, then pattern generalization and abstraction, kind of a pair, and finally, algorithm design.
Okay, let's jump right in. First step, just getting organized.
Right. The foundation is decomposition. It's really the process of first understanding a complex problem and then, well, breaking it down methodically into distinct, smaller pieces. If you can't describe the parts, you definitely can't solve the whole thing.
And the sources give us this great, really relatable example. Not technical at all. Say your goal is just making an amazing jerk chicken dinner. You don't just write make dinner on your list. That's uselessly vague.
Exactly. You decompose it. You realize cooking is just one part. It starts way earlier. You have to work first, right, to get paid. Only then can you buy the chicken. Then clean it, season it, cook it, eat it, and finally sleep. That structure, that whole sequence, that's decomposition in action.
I like that one because it also shows, well, it's not always perfectly step-by-step, is it? Like, what if I use a credit card? I could buy chicken before I technically get paid.
Yeah.
Does decomposition still work if the steps aren't, strictly sequential?
Oh, absolutely. And that's a really key insight. Decomposition forces you to identify the dependencies, what has to happen before something else can. Even if the timing shifts a bit,
Okay.
you still can't cook the meat before you buy the chicken, right?
Yeah.
So even for a programmer trying to, say, get a name and save it to a file, they decompose too. They know logically you can't write to the file before you open the file. The dependency dictates the structure.
Got it. So you take this one big vague thing and turn it into a set of actual tasks, the edges of the pieces. Okay, so once we have those pieces, the next step, pattern recognition, feels less about solving and more about looking back, like smart research.
Precisely. Pattern recognition is all about spotting the common threads, the similarities, the features, maybe even the differences within those pieces you just decomposed, or maybe across different problems you've already solved.
Why? What's the point?
Efficiency. It's all about efficiency. If you spot a trend, something you've done before, you don't reinvent the wheel, you reuse it, you generalize, you save time and effort.
This is huge in business, right? I mean, think about, like, the video game industry. Those big annual franchises, we all know FIFA, Madden, a new one drops every single year. You might think they're rebuilding the whole game each time.
But they couldn't possibly. They'd never make the deadline.
Right.
They use pattern recognition heavily. They see that, okay, 95% of the core stuff, the game engine, the online code, even the basic layout of the start menu, it's fundamentally the same as last year's game.
The pattern is continuity. So instead of coding a whole new menu system from scratch, which would take ages,
they recognize the pattern, they tweak maybe the colors, update the player rosters, the surface stuff, but they leverage that existing code, that existing structure. That ability to spot repetition saves so much time, whether you're launching a product or just planning your meals for the week.
Okay, so we've broken the problem down with decomposition, and we've looked for similarities using pattern recognition. Now we move to the stage that really enables scale, pattern generalization, and abstraction.
Abstraction. That word sounds a bit academic, maybe a little fuzzy, but it's actually super practical. It's about deliberately ignoring stuff, filtering out the details that don't matter and just representing the essential bits in a simpler way.
It might be the most powerful part of CT, honestly. The key idea is that abstraction is how you manage complexity, how you scale things up. In programming, for example, we abstract to figure out what really matters for the solution.
Well, things like the variables, the data that changes, the fixed constants, the key processes or steps, the necessary inputs and outputs, everything else, like the color of the wires inside the computer, the specific brand of hard drive, what font the developer likes.
Irrelevant.
Totally irrelevant. It gets filtered out, ignored.
And that focus is why it's so important, not just for writing cleaner code, but for teamwork too, right?
Yeah.
If a project is well abstracted, different people can work on different simplified parts at the same time. They don't need to know every single tiny detail of everyone else's work.
Exactly. It promotes reusability and makes collaboration possible on big projects.
Right.
You know, we use abstraction all the time in daily life without thinking about it. The classic example is driving a car.
Right. When I get my car, I just need to know about the steering wheel, the gas, the brake. That's kind of my interface with the car.
That's exactly it. That's the abstraction, the incredibly complex mechanics of the engine, the algorithms running the anti-lock brakes. All that stuff is hidden away. Abstracted.
Yeah, if I had to understand thermodynamics just to drive to the shops, I'd never leave the house.
Precisely. And the manufacturer can improve the engine year after year, make it more efficient, whatever. But as long as your interface, the pedals, the wheel stays the same, you don't need to relearn how to drive. The abstraction holds.
That's really powerful. The complexity is managed, hidden, but the function is still there. Okay, what about the Google Maps analogy? That one's good too. When I use the app, I just need the route, the turns.
You don't need, nor do you want, the detailed elevation profile of every single street you pass, or the complete traffic history for every intersection for the last 10 years, or the name of every little side road.
It'd be overwhelming. Just noise.
Exactly. It's unnecessary detail for the task at hand, which is just getting from A to B. Google Maps abstracts the messy reality of the entire road network down to the essential path you need. That's abstraction making a complex system usable.
Okay, so let's recap quickly. We took a big problem, used decomposition to break it down, used pattern recognition to find similarities, used abstraction to simplify and focus. Now, the final piece of computational thinking, algorithm design.
Right. This is where the rubber meets the road, so to speak.
Yeah.
Algorithm design is about creating the actual specific step-by-step plan to solve that simplified, abstracted problem. This is where you really focus on making the solution correct, fast, efficient.
And why is that so important? I mean, if it solves the problem eventually.
Well, a bad algorithm might get there, sure, but it could be incredibly slow, use way too many resources, cost more money. An efficient algorithm saves time, saves resources, gets the right answer reliably. It's crucial. And the sources highlight two main tools we use to design these algorithms, pseudocode and flowcharts.
Let's start with pseudocode. You called it a textual blueprint. So it's like writing out the instructions in English almost.
Oh, kind of, yeah. Think of it as a rough draft for the logic, written in plain text before you get bogged down in the specific syntax of a real programming language like Python or Java. It's meant to be readable by humans, but it does follow certain conventions.
Conventions like P-words.
Exactly. Standardized words that mean specific things, like input for getting data, output for displaying results. Logical structures like while or for to describe doing something repeatedly, and the really fundamental one for decisions. If, then do this, else do that.
So if, then else just signals a choice point.
Universally. Anyone reading it knows, okay, here, the process might go one of two ways depending on some condition, whether you're planning a budget spreadsheet or coding a rocket guidance system, if then else means decision.
And it clearly maps out the logic, even for simple stuff, right? Like finding the area of a rectangle.
Super simple. Your pseudocode would just be input length, input width, calculate area, length width, display area, 4 clear steps.
But it's powerful enough for complex things too. The sources had that example about generating, 20 unique usernames?
Yeah, that's a great example of where pseudocode shines because the logic gets tricky fast. Seems simple. Make usernames for new students. But wait, you need age validation. They have to be between 5 and 18.
Okay.
And crucially, you have to check for duplicate usernames. What if 2 students have the same name? That check is surprisingly complex to get right automatically.
Right, let's trace that logic.
Yeah.
So the basic idea is to stick together the first name, last name, and age, like John Smith 12.
Right.
But what if John Smith 12 already exists in the system?
This is where the algorithm gets clever, as described in the pseudocode. If it finds a duplicate, it doesn't just give up or throw an error. It automatically tries a variation. It adds 1 to the age value it used.
Oh.
So then tries to create and check John Smith 13. If that exists, maybe tries John Smith 14, and so on. It iterates. It's a loop built into the pseudocode logic to guarantee everyone gets a unique ID without a human having to intervene every time.
That's smart. Really elegant problem solving, just laid out in text. Okay, so if pseudocode is the text blueprint, flowcharts are the pictures, the visual diagram.
Exactly. Flowcharts represent the exact same logic, but visually, using shapes and arrows.
And why use them? Isn't pseudocode enough?
Flowcharts are fantastic for communication, especially with less technical people. Humans are visual creatures. They make complex processes much easier to grasp at a glance. You can often spot bottlenecks or weird logic paths just by looking at the flow.
Makes sense. And the shapes aren't random, right? They have specific meanings. You mentioned 3 key ones.
Well, 4 really essential ones. The oval shape, that's always your start and your end point. Tells you where the whole process begins and finishes.
Okay. Start and oval.
Then the rectangle. That's for any action or process step, like calculate area or season the meat. Something is actively happening.
Got it. Rectangle, action.
The diamond. This is crucial. It represents a decision, always has a question inside, and always leads to 2 paths coming out, usually labeled yes or no, if then else in visual form.
Diamond, decision.
Yes. And finally, the parallelogram. This one's specifically used for input or output operations, getting data in, like input answer, or sending data out, like display username.
Okay, parallelogram for I/O. So if we map out that example checking if the answer to what's the best subject is computer science.
Right. You'd start with a start oval, arrow to a parallelogram for input answer, arrow to a decision diamond asking is answer computer science, then 2 arrows out, one labeled yes, leading to an output parallelogram saying correct, the other labeled no, leading to one saying try again. Both those outputs would then lead to the final stop oval.
Perfectly clear. No ambiguity. You just follow the arrows based on the decisions. Hashtag tag outro.
Yeah.
Wow. Okay. That was quite a journey through computational thinking. Let me try and boil it down. You start with a big, messy problem. You use decomposition to break it into smaller, manageable pieces. Then you use pattern recognition to look for similarities, things you've seen before, to be more efficient.
Yep. Avoid reinventing the wheel.
Then abstraction. That's about filtering out all the noise, focusing only on the essential details, the core variables and processes.
Simplifying reality to build a model.
And finally, algorithm design, using tools like pseudocode or flowcharts to create the precise step-by-step instructions to actually solve the problem based on that simplified model.
That's it. Those 4 components are the bedrock.
Yeah.
And as the sources suggest, once you grasp these, the logical next step is to really dig into the specific standard methods and techniques used to develop good, efficient algorithms. How do you actually build those structures well?
Right. That's a whole other deep dive. So here's a final thought for you, our listener, to maybe chew on. Think about a major decision you have coming up. Not a technical one, maybe planning a big move or choosing a new career path. If you treated that decision like an algorithm,
Interesting.
which of these 4 CT components, decomposition, pattern recognition, abstraction, algorithm design, would you lean on first to just start tackling it? And could actually mapping out that flow before all the emotion and overwhelm kicks in make the final outcome feel, well, not just better, but maybe even predictable?
That's a fascinating question, something to think about.
Definitely. We'll leave you with that. Thanks for joining us on The Deep Dive, and we'll see you next time.